Good morning, afternoon, or evening, cats and dogs. Today's video comes from the lesson 7.4 guided notes on scale drawings. We first want to talk a little bit about where in real life we see scale drawings and models. And you can see some examples in your guided notes. For example, model airplanes or perhaps a drawing of an airplane. When people build houses, when construction workers come in to build houses, or a planning manager or construction manager comes in to build a house, they often have blueprints, which are going to be some sort of scale drawing. Perhaps sometimes they even create scale models of those items. Nowadays, we do tend to use a lot more computer animation for those kinds of things as well, but we also have those blueprints typically either on paper or on a computer system. We can also see some other examples here. For example, when you pull up a map on your phone, so this is a map of Central Dauphin Middle School, we can see that this is really a scale drawing or a scale model of what the actual roads look like. So it looks like a pretty short distance here along Locust Lane where our school is, but we know it's a pretty long distance or a pretty large distance in real life. In our science textbooks, you might see scale drawings or models of DNA or an atom. So these are times when we might actually enlarge something that's too small for us to see just by the naked eye. We also have figurines or statues sometimes that may be real life sized, but they might also be scale models of the actual figure. What's really important for us with scale drawings and models, and I do want to mention this, I think it's the next slide, is we want to make sure that the lengths and widths of our model or drawing, whether it's on paper, whether it's an actual model itself, whether or not it's a computer diagram or a computer image that we're creating, we want to make sure that the dimensions are proportional to the actual figure. This might have happened to you sometimes when you took a picture, and this is actually the Alamo down in San Antonio, Texas. But if we take a picture and we try to either enlarge it or make it smaller, and somehow we end up accidentally stretching it out, those dimensions don't stay proportional to the original figure. So it might look stretched out like this, it might look stretched out like this, but if they're not proportional, it may end up messing a little bit with our picture so it doesn't look exactly the same. So on this first page of our guided notes, we have a lot of important information here about what scale drawings and models are, and then the two main things that we're asking ourselves to find with regard to scale drawings and models. It's a pretty simplified lesson. It's something you'll see again. If you take geometry, you'll also see this again at a little bit more of a complicated level, since I know I taught geometry a few years ago, and this is something we covered there too. So you'll see another other lessons, other years. It's also something that depending on what career you go into, if you're an interior designer, if you do want to be a contractor in terms of either renovating or doing some work in homes, you're probably going to be working a lot with scale drawings or models. If you're a scientist, a lot of times you're going to be working with scale drawings or models that are actually enlarged. So lots of careers are going to use these things. So a scale drawing or model, I know we already showed you several examples, is used to represent an object that is too small, like that example with DNA or an atom, or too large to be drawn or built at actual size. So again, before construction workers go out and build homes or bridges, a lot of times they're going to have a scale drawing or model of that. Again, a lot of times that stuff's done on computers. It's used, even you see a lot of managers walking around with iPads now. So, we've definitely come a long way from where we were 10, 15, or even more years ago. Some examples include model airplanes, buildings and cars, blueprints or other plans for construction, and maps. Again, most of this is technologically savvy at this point. We don't necessarily use paper maps anymore, but we do use GPS systems. The lengths and widths of the model are proportional to those of the actual figure. We've worked with proportions several times before. This is really important because, again, if they're not, we get either that stretched out version, either horizontally stretched out or vertically stretched out. So it's not going to look exactly the same. And that would definitely pose some problems for scientists, or would pose problems for building contractors. Now, the two main things that we're going to ask you to find in this lesson are scale and scale factor. So when we talk about scale, scale is determined by the ratio of a given length on the drawing or model to its corresponding length on the actual object. We will always do the drawing measurement or the model measurement to the actual measurement. So it's going to be something equals something. The units of measure do not need to be the same for scale. For scale factor, the units of measure will need to be the same. So that's going to be really important for us. An example would be 1 inch equals 3 feet. Now we know 1 inch isn't truly equivalent to 3 feet, but 1 inch on the model represents an actual length of 3 feet. We have to have some sort of scale on that drawing to know what those measurements actually represent. Our scale is always going to be written as in the form 1 unit equals some other number. So you might sometimes see like 2 centimeters equals 5 meters or something like that. But we will always write it in terms of 1 unit on that left-hand side of your equal sign. The second thing that we're going to ask you to find is scale factor. And scale factor is a fraction. Scale factor, fraction, they both start with F. When the scale is written as a fraction in simplest form, again with the same units of measure. So our first example, example 1, is pretty easy. Suppose a scale model has a scale of 2 inches equals 16 inches. This is where I said sometimes your scale might be written with 2 inches equals something. We could write it in terms of 1 inch as well. The scale factor, which will be a fraction, is the model 2 inches over the actual 16 inches. Because they have the same unit of measure that I can get rid of, we get 2/16, but we do want to reduce that to 1/8. This means that the scale model or drawing is 1/8 the actual size. Now, example 2 is even more important. I'm going to highlight this one in green. So suppose a scale model has a scale of 1 inch equals 3 feet. The scale factor will be 1 inch over 3 feet, but I need to convert my 3 feet into inches. Generally, we'll convert our larger measurement. There's 12 inches in a foot. 3 times 12 is 36 inches. Now that I have the same unit of measure, I can get rid of them, and my scale factor is 1/36. And again, the 36 comes from the fact that there are 36 inches in 3 feet. It's equivalent to 3 feet, but we're writing it in terms of the same unit of measure. So 2 main things right here, even though we'll also see some word problems that we'll talk about. Scale, which is model equals actual. Scale factor is a fraction, but the units of measure have to be the same for scale factor. So let's get right into our examples. So numbers 1 and 2. Number 1, it says on a scale model of a building, the highest point of the building is 14 inches. The actual height of the building is 175 feet. What is the scale of the model? We want to read carefully and look at what it's asking us to find. The scale is going to be model equals actual. We know that the model of the building has a highest point of 14 inches. So that's going to go on the left. We know the actual height of the building is 175 feet. That's going to go on the right. So I'll write 14 inches equals 175 feet. But I want to get it in terms of 1 inch. So I'll divide both sides by 14. 14 divided by 14 is 1 inch. 175 divided by 14 is 12.5 feet. So 1 inch on the model represents 12.5 feet in real life. Let's take a look at number 2. On a scale model of a building, the highest point of the building is 14 inches. The actual height of the building is 175 feet. What is the scale factor? So again, we want to pay attention to what it's asking us to find. Remember a few years ago, I was reading through this question and thought, oh my goodness, I put the same question twice. But this one's asking us for the scale factor. So this is going to be model over actual. So our model measurement is 14 inches. Which we've already highlighted before, but I'll highlight it again here. So the scale model, the highest point is 14 inches. Actual height is 175 feet. But remember for scale factor, the units of measure have to be the same. So I need to convert 175 feet into inches. So I'm going to do that by taking 175 times 12, and that's going to get me 2,100 inches. So I replace 175 feet with 2,100 inches. My units of measure are now the same. And then I just plug into my calculator 14 over 2,100, and it simplifies it to 1 out of 150. Now, I don't know if anyone was thinking, if I go back to this answer from number 1, 1 inch equals 12.5 feet, could I write 1 inch over 12.5 feet and then convert them to the same unit of measure, I could. So if I had 1 inch on the top, 12.5 feet on the bottom, so just kind of creating a fraction here for us. If I set this up, 12.5 feet is equivalent to 150 inches. Take 12.5 times 12. This then equals 1 inch out of 150 inches, which is just 1/150th. I'm not going to type it again, but we now have the same unit of measure. We don't need to simplify it. We get the same solution. So we could use the scale that we came up with in number 1, or we can use the original values that were given to us. We should get the same scale factor. All right, let's take a look at numbers 3 and 4. You can see my random division symbol that I was copying down here as well. So number 3, on a set of landscape plans for a new garden, the length of the garden is 18.5 inches. If the actual length of the garden is 111 feet, what is the scale of the plans? So again, it's asking us for the scale, so that's going to be model equals actual. We know that on the plans, that happens to represent our model. The length of the garden is 18.5 inches. And then the actual length of the garden is 111 feet. So that's going to go on the right-hand side. So 18.5 inches is the model length. 111 feet is the actual length. Divide both sides by 18.5, or both numbers by 18.5, and I get a scale of 1 inch represents 6 feet. Now my suggestion for this one, for number 4, when you go to find the scale factor using the same information, this scale is way easier. In our last question, both numbers were not so bad, but we've got 18.5, so we have a decimal number of inches, 111 feet, which is going to be quite a few inches. I suggest using the 1 inch equals 6 feet. So again, same information in number 4. Feel free to read through that. So we've got our model equals actual. Let me go ahead and slide this down. It's 1 inch on the model, represents 6 feet in real life. Now, could you do 18.5 inches over 111 feet? Absolutely. That's a lot more work, though. Convert your 6 feet. I'm going to highlight this in yellow. Convert your 6 feet into inches. 6 times 12 is 72 inches. We now have the same unit of measure, so we can get rid of our inches. And our final answer is 1 out of 72. For the scale factor, by the way, it's just a common mistake I see from students. You don't need a label on your final solution. It doesn't matter whether your units of measure are inches, feet, meters, miles. We know that our plans are 1/72nd the actual size, no matter what measurements we're looking at. All right. Let's go ahead and take a look at numbers 5 and 6. Number 5, if the scale of a blueprint of a building is 1 inch equals 8 feet, that should be a comma, and then a lowercase w. What is the scale factor? This one's asking us for the scale factor. That's a fraction. Model over actual, which is 1 inch over 8 feet. 8 feet is 96 inches. Take 8 times 12 to get 96. Now that we have the same unit of measure, our final answer is 1/96. Again, we want to make sure for scale factor, which is a fraction, units of measure need to be the same. Number 6, Drew is putting in a new patio in his backyard. On the set of plans that he has made, 1/2 inch represents 8 feet. What is the scale for his plans? So that's model equals actual. We know that on the set of plans he has made, we've got a 1/2 inch, so that's going to be our model. That represents 8 feet. That's actual. So we can write 1/2 inch equals 8 feet, divide both sides by 1/2, or multiply by 2 will get us that 1 inch equals 16 feet. We do need labels for the scale. Scale factor, we do not. All right, number 7. In an illustration in a textbook, the length of a fly is 4 inches. The actual size of an average fly is 0.2 inches. What is the scale of the illustration? So scale is going to be model equals actual. I want to make sure. I feel like I copied and pasted this from pre-algebra and I had a mistake that I fixed. So let's see if I fixed it here or if it still has the wrong solution. So we know that our model is the illustration in this case. The length of the fly is 4 inches, so that's going to go on the left-hand side. Ah, good, I did fix it. Okay, so the model is 4 inches. Actual is 0.2 inches. I think I had them backwards previously because this is one where we're actually enlarging it, which is a little bit different. Just silly me making a mistake. It happens sometimes when you're typing things in quickly. So we have 4 inches on the model, and that illustration represents 0.2 inches in real life. Divide both of these numbers by 4. So we get 1 inch on the model represents 0.05. When I take 0.2 divided by 4, that gets me 0.05 inches. So 1 inch on the model represents 0.05 inches on the actual fly. And this one looks a little different because we're actually enlarging this. This is something we want to enlarge to be able to see a little bit better. So that's why you notice that scale looking a little different. Number 8, also a typo here. It says if the scale is 10 inches equals 1 foot, that should be comma and a lowercase w for what is the scale factor. Remember that scale factor is a fraction. We've seen lots of examples of this. There's also an extra practice sheet that goes along with this too if you need some more practice. So model over actual is going to be 10 inches over 1 foot. Replace 1 foot with 12 inches so you get the same unit of measure. Now that we have the same unit of measure, we just simplify 10/12, which is going to reduce to 5/6. All right, number 9 is a multiple choice question. I like to mix these in every now and then so we get some practice with it. The scale on a set of blueprints is 3 inches equals 4 feet. What is the scale factor? Go ahead and pause the video, give this question a try. Scale factor, of course, is a fraction. Which of these is correct? So hopefully it's fresh in your mind that you're not choosing C, but if I gave this to you maybe at the end of the unit, you might choose C. C is not correct though, because we need to get the same unit of measure. So we have 3 inches over 4 feet. We need to convert feet into inches. 4 feet is 48 inches. 3 inches over 48 inches reduces to which answer? Hopefully you're thinking or said 1/16, which is letter A. All right, so I do have 2 questions I want you to try on your own. So again, pause the video, give these 2 questions a try when you're ready, restart the video, and we'll take a look at your solutions for these. All right, so number 1, Julius Caesar was 67 inches tall. A scale model of Caesar is 5 inches tall. What is the scale? So we want this to be model equals actual. We know that the model is 5 inches tall. So that's going to go on the left-hand side. And then Julius Caesar was actually 67 inches tall. So we'll have 5 inches equals 67 inches. Divide both sides by 5. And we get that 1 inch on this model represents 13.4 inches in real life. Number 2, the scale of the blueprint of a building is 2 inches equals 12 feet. What is the scale factor? So that's going to be a fraction. So we put 2 inches over 12 feet. 12 times 12 is 144 inches, so we get 2 inches out of 144 inches. Now that we have the same unit of measure, we can get rid of these guys. 2 out of 144 simplifies or reduces to 1/72. All right, so our next set of questions really could have gone in our last unit, could have gone here with scale factor. In fact, pre-algebra sees it in the same unit as proportions, because I think the best way to do these problems or approach them is basically to use proportions to find our solution. So it says find the length of each model, then find the scale factor. So we're given a scale on each of these. Oftentimes the scale is given somewhere on that model itself. I'll highlight each of those scales in yellow. We're going to use that to help us find, we're given the actual length of this. It looks like a little bit of a subway train or just a train in general. We're given the actual length of 60 feet. We want to find the model length, given that the scale is 1 inch represents 8 feet. So I set up a proportion. It's not the only way to do it, but I think it's one of the easiest ways. We're talking about inches and feet, so I put inches over feet. Could you put feet over inches? Sure. I just kept it in the same order that the scale is in. So 1 inch on the model represents 8 feet in real life. we want to figure out how many inches on the model represents 60 feet in real life or on this actual train that we have. Do you remember how to solve these things? We cross multiply. Hopefully you remember that. So we take 8 times x, 1 times 60, and set them equal to each other. So I have 8 times x is 8x, 60 times 1 is 60. Divide both sides by 8, and we get that the model length of this thing is 7.5 inches. Now it does say to find the scale factor in the direction. So take your scale, 1 inch equals 8 feet, write it as a fraction, 1 inch over 8 feet. 8 feet is 96 inches. How did I get that? I took 8 times 12 since there's 12 inches in a foot. Once you have the same unit of measure, you can get rid of those. Our scale factor is 196. So our model subway train or train that we have is going to be 1/96 actual size. All right, so the next one we have this arch. I forget what the name is, and I'm not going to look it up right now. Maybe like the Gateway Arch or St. Louis Arch. We have this arch here, and we know that it's 192 meters tall. We're given a scale of 1 centimeter equals 4 meters. We want to find the model height of this. I know it says find the length of each model, but we're really looking at the height of this thing. So I set up a proportion, centimeters to meters. 1 centimeter on the model represents 4 meters in real life. We want to figure out how many centimeters our model of this arch is. We know it's 192 meters in real life. So cross multiply. 4 times x is 4x. 192 times 1 is 192. Divide both sides by 4. And our model is going to be 48 centimeters tall. Now, scale factor, we haven't really done a lot of conversions between centimeters and meters. So let me go ahead and delete this so we can take a look at it. We've got 1 centimeter to 4 meters. There's 100 centimeters in a meter. That's the good thing about the metric system is it's all based on powers of 10. So take 4 times 100 gets us 400 centimeters. Now that we have the same units of measure, our scale factor is 1/400. All right, our last one is an alligator or crocodile. I don't know the differences between them. I know there are some differences, but we're going to set up a proportion. So inches to feet, 2 inches on the model represents 1.5 feet in real life. We want to figure out our model length of this alligator or crocodile. We know it's actually a huge alligator or crocodile at 13.5 feet. So cross multiply, we have 1.5x, and 2 times 13.5 is 27. Divide both sides by 1.5, and we get that our model is 18 inches long. For scale factor, we have 2 inches over 1.5 feet. 1.5 feet is 18 inches. 1.5 times 12 is 18. Now that we have the same unit of measure, 2/18 does reduce to 1/9. So it's just a little bit of an application of scale and scale factor to some more real life kind of problems. All right, let's take a look at numbers 13 and 14. Number 13, it says a set of landscape plans shows a flower bed that is 6 3/4 inches wide. The scale on the plans is 1 inch equals 4 feet. What is the width of the actual flower bed? So this is pretty similar to what we already saw just without the pictures. I did set up a proportion. This is not the only way to do it, where we're comparing inches to feet. We're given a scale of 1 inch represents 4 feet, so 1 inch to 4 feet. Now we are given that the set of plans is 6 3/4 inches wide, so that goes on the top with the inches. That makes that a little different than our last one, but it makes our work pretty easy here because 1 times x is just x, and we just need to do 4 times 6 3/4. So that's going to end up getting us 27 feet. Some of you might have recognized, well, if I know that 1 inch represents 4 feet, and I know that this flower bed is 6 3/4 inches wide, can I just take 4 times 6 3/4? Yes. A proportion helps you to figure out whether you're multiplying or dividing those numbers, but we are really just multiplying them. Kind of similar in our next one, except our scale is not in terms of 1 inch, so it makes it a little bit more complicated. Number 14, the blueprint of a building shows that its height is 11 2/5 inches. If the scale on the blueprint is 1/2 inch equals 3 feet, what is the height of the actual building? So again, I set up a proportion for this, and I used 0.5 for a half, but our scale is ½ inch represents 3 feet, so 0.5 over 3. We know that the blueprint of our building is 11 2/5 inches high, so I put that on the top with the inches. Now you could convert your scale into 1 inch, like if a ½ inch represents 3 feet, that means that 1 inch represents 6 feet. And so you could really just take 6 times the 11.25 to find your solution as well. But let's go ahead and cross multiply here. So we have 0.5 times x is 0.5x. We still need to take 3 times 11 2/5. That's going to get us 0.5x equals 34 1/5. Divide both sides by a half, or 0.5. So I took 34 1/5 divided by 0.5, and that got me 68.4 feet. You might get 68 2/5 feet. It's the same thing. All right, so our last type of question here is where we have what we call similar figures. These are figures that have the same shape, but they're different sizes. So you can see that the triangle on the right is bigger than the triangle on the left, yet they kind of look the same. So I want to figure out what this x is. What I suggest doing for a problem like this is matching up sides that correspond. Like this bottom side corresponds with this, and the right sides correspond with each other. So I set up a proportion. It's not the only way to do it. You could also find the scale factor and use that to help you figure out what x is, but I think this is the easiest. So I wrote 4 over x, my green sides, equals 2.5 over 6.25. You could also write x over 4 and 6.25 over 2.5. You could even do 4 over 2.5 equals x over 6.25. There's a lot of ways to set up the proportions. I know we talked about that when we did proportions, I think in our last unit. So there are other ways to set this up. This is just the most simplified way, is match up these corresponding sides and then set up your ratios accordingly. Let's go ahead and cross multiply. So we're going to do 2.5 times x, which is 2.5x. 4 times 6.25 is 25. Divide both sides by 2.5, and we get that x is 10 inches. Now we've got two similar rectangles in this case, so I just matched up my corresponding sides again. The bottoms correspond with each other. Luckily, we're not going too complicated. When pre-algebra did this, we sort of rotated some of the figures, so it was a little harder to match up those corresponding sides. We're going to keep it pretty simple here for now. You'll see this again in future classes, maybe in 8th grade, but definitely in geometry, you will see this. So I wrote 2.5 over x, my left side to my left side, equals 6 over 10. Now notice how, since I started with my smaller rectangle, I have to start with my smaller rectangle in my second ratio. I could have also done x over 2.5, which means I would have to have 10 over 6. Cross multiply, we get 6 times x is 6x. 2.5 times 10 is 25. Divide both sides by 6. We do get a really weird decimal for this one. I want to make them not always work out nicely. You get 4.16 with the 6 repeating meters. All right, this is something we're going to see a lot more of in class. There's a lot of different topics in this with some proportion questions. We also talked about scale and scale factor. Remember, scale is model equals actual. Scale factor is a fraction. I will be giving you an extra practice sheet, very short, just a half sheet that goes with this if you're looking for some additional practice outside of class as well. Thanks for listening.